Hello. Today we begin 4.2, What Derivatives Tell Us. We'll use derivatives to analyze maxes and mins, try to figure out where those maxes and mins occur. There are two techniques for figuring out where the maxes and mins are. We can use the first derivative test, or we can use the second derivative test. This lesson will be split into 2 days, and today I'll cover the first derivative test, and in a future video I'll talk about the second derivative test. All right, let's begin. Suppose we are given a continuous function defined on a closed interval from a to b. This function has extrema, some maxes and mins. And there are two types of extrema. There are local maxes and mins and absolute maxes and mins. So I have an absolute min here, an absolute min there. And I have local maxes and mins. Local maxes and mins won't ever occur at endpoints. So our goal, use derivatives to locate local extrema. In a previous lesson, we located the absolute max and min using derivatives, but now we turn our attention to local max and min. Recall, a critical point is an x value, c, that is not an endpoint, and either f prime of c equals 0 or f prime of c does not exist. So C1, C2, C3, C4, C5, these are all critical points, places where either the derivative is 0 or places where the derivative does not exist. Every local extremum occurs at a critical point. Is that true? Let me identify where are my local extrema, local max, local min, local max, and yes, look at that. It occurs at critical point. Every local extremum occurs at a critical point. But not every critical point has a local extremum. For example, C1 is a critical point that does not correspond to a max or min, and C5 is a critical point that does not correspond to a max or min. The function has to be either increasing or decreasing between critical points. It doesn't actually change direction. Between a and c1, the function is increasing. Between c1 and c2, increasing, then decreasing, increasing, decreasing, decreasing. And there's a correspondence between whether the function is increasing or decreasing and what the sign of the derivative is. If my derivative is positive, then the function is increasing. Do you see, let's see, f prime of x, that in this first interval between a and c1, my first derivative is positive. If I pick any point on the curve, it'll have a tangent line with a positive slope. Similarly, between c1 and c2, my first derivative is all positive. Then I have negatives, positives, negatives. If f prime is less than 0, then f is decreasing, and f prime can change sign only around critical points. Here is the first derivative test. Here's how we use the first derivative to help us find the location of local maxes and local mins. Suppose that c is a critical point of my function f. If f prime changes from positive to negative as x increases through c, then we have a local max at c. For example, consider the values of f prime of x around c2. First, before c2, it's positive, and then after c2, it's negative. So as x moves through c2, f prime of x changes from positive to negative. The function f changes from increasing to decreasing, and I have a local max. There's a similar statement for local mins. If f prime does not change sign, there's no local max or min. And we can see that, for example, on the right, between 4 and 5, my first derivative is negative, and then after 5, the first derivative is negative again, and there's no local max or min. Let's say we are given a function symbolically. How can we find the local extrema? So in this example, locate the local extrema of f of x equals x cubed minus 27x minus 20. So step number 1, find the critical points. F prime of x equals 3x squared minus 27. And so let's solve f prime of x equals 0. We need to solve f prime of x does not exist, but f prime of x is a polynomial, so it exists everywhere. Is f defined around plus or minus 3? And here I look at my original function. And my original function is a polynomial, so it is defined everywhere. Yes. So I found my critical points. My critical points are x equals plus or minus 3. The second step is to make a sign chart. Here's what I mean. Make a little segment of the x-axis and put down the x values where the critical points occur. Say -3 and +3. Now, we're going to determine the sign of f prime of x around those. So f prime of x. Is it positive, negative, 0? Well, the derivative at -3 is 0, and the derivative at +3 is 0. I can put those down. What if I take a number between -3 and +3, and I put it into my derivative? So here's the derivative. 3x squared minus 27. If I plug 0 into my derivative, the answer is -27. I don't even really care about the fact that it's -27. I'm just interested in the fact that it's negative. So any x value I plug in between -3 and +3 has to be negative. This is what we talked about earlier when we said that the sign can't change unless it changes across a critical point. There's no critical point between -3 and +3. So once I find the sign of one number between there, I know them all. How about to the right of 3? What if I plug in a number bigger than 3 into my first derivative? Say 5. So if I plug 5 in there, 3 times 5 squared minus 27, well, that's positive. Or if I throw 1,000 in there, 3 times 1,000 squared minus 27, definitely positive. So all of the derivatives for x values greater than 3 are going to be positive. And now, lastly, let's consider the negative portion. What if I throw in a negative number less than -3 into my first derivative? Say -10, 3 times -10 squared minus 27. -10 squared is positive 100. Yeah, so that whole thing is definitely positive. And at this point, I know something about my original function f. I know it has to be increasing, then decreasing, then increasing. And now, using my first derivative test, it looks like at x equals -3, there's a max, and at x equals +3, there is a min. All right, so you have all the information you need at this point to try the worksheet problems and try the homework problems. Do your best, get to it, and let me know if you have questions.